I'm Dirk Ohlerich, Chaos of Farbrausch, and I'm going to talk about multithreading, especially for graphics. I'm going to a little introductory talk about multithreading and task stealing. And then I will talk about all the problems that you have if you want to apply it to graphics with dependencies, inconvenient output buffers, my favorite, pipelining, and priorities. Why multithreading? Multithreading for graphics is, of course, multithreading for speed, because we are only interested in making, or primarily interested in making our applications run faster. So if you create a bunch of threads, things don't automatically get faster. They only get faster if you have actually multiple cores running there. And so it doesn't really make any sense to have there more threads than you have cores. Because if you're creating threads on its own, only creates more problems, more overhead, more stuff to worry about, makes everything complicated. And the only reason to actually bother with it is that we have multiple hardware threads on which we can run our software. We have to think as a thread as some kind of device that we can use to use some actual hardware. If we are not using threads and we have a quad-core machine, there are 3 cores just sitting there and wasting energy. If we use threads, we can actually use them. For instance, if you build a web server and you say, well, let's use this wonderful technique called multithreading and have a thread per connection, that maybe make your design a little bit simpler, but it is a total waste of resources because you will spend so much time in the operating system overhead switching between different threads. If you're building a high-performance web server, you would never think about an idea like that. There's also another reason to use threads, which is on the old school computers, Amiga C64, we had interrupts. And if we had something to do very urgently, like the music, or the hardware would give an interrupt, and then you can have your code running. Then your code runs. But on a modern operating system, you as a programmer are not trusted. So you cannot use the interrupt directly. It's just that the hardware will fire up a signal, and then the operating system will signal your thread that it can run. But that's a totally different way of multithreading. Like if you have an audio thread, or a network thread, or a streaming thread, you want to react on things in real time. That's a completely different reason for streaming than what I'm talking, different reason for multithreading than I'm talking multithreading for performance. So now that we have made clear that we only have 1 thread per hardware thread, 1 thread per core, so to say, we still have to model our problem space things. Like if you have a game, you have cars and effects, and you have some way to represent these things. And you can call that a task or a job. And then you can create hundreds or thousands or tens of thousands of tasks or jobs. I would call them tasks here. And you need an engine that distributes all those tasks to the hardware threads. We call it a task scheduling engine. And I'm going to talk about how to build such a task scheduling engine in a specific way. So basically, we have 1 main thread, of course, the one that gets started with a program, the one that has full control over the DirectX device or OpenGL, the one that defines all the tasks that have to be executed. And then we have worker threads that do the work. The main thread can also join in if there's nothing left to do to help the worker threads. And then maybe we have an audio thread or network thread caring about all these real-time issues. So what is a task? Actually, a task is nothing more than a deferred function call. You have a function pointer, we have some parameters, and possibly in these parameters there are pointers to buffers, to memory locations. And all these tasks, we put them in a pot and then hope that our task scheduling engine will execute them all in parallel. And actually that will happen in a random order. And that's the first big problem we have. If you put all our tasks in a big bag and distribute it to all our threads, there's no way in telling in which order these tasks will be executed. And I highlighted here read and write buffers. Of course, if one of these tasks writes to a memory location that is possibly read by another task, and we don't know in which order these tasks are executed, we have a big problem. We need a way to express dependencies. That was the second topic of the talk. Right now, we have a problem with dependencies that we will have to solve later. Before I go into the design of such an engine, let's make a little talk about how we do multi-threaded programming. The operating system usually gives you a rich set of primitives: semaphores, mutex, critical sections, event queues, all these wonderful techniques to express how you're multi-threading, how your task communicates. The basic problem is two tasks want to modify a complex structure, like some kind of tree or whatever entity you have. And if they both access the same thing at the same time, it will be total confusion. So what you have to do is you have to find a way to lock that structure to a certain thread. And as long as that thread is working on that structure, no other thread can get the lock. And once the original thread has finished, other threads can get the lock and work on. And this way, you can make sure that the threads are not overwriting each other's data. And the problem with all those wonderful primitives to do the synchronization given to us by the operating system is they are all completely useless because they yield. The operating system thinks, well, there are many programs running on my computer, and they have all plenty of time to do their work. And so every time a thread has to wait, it gives up to another thread, which might be doing very important things like indexing your files and downloading stuff from microtorrent, or the malware that's sending out spam mail to everyone. But this is not what you want. It can take milliseconds before you get back the control to your own thread. And you want to run in 60 FPS, that means 16 milliseconds. And if you have to wait for milliseconds, you can't do that much, can't do that often in a frame. So we don't want to use any of these operating system functions that potentially give up to another thread. What we want to do is to use something called a spin lock. We want to, if I'm a thread, if I see that I can't access that resource, I just turn in circles until I can and don't yield to other operating system threads. Well, there are this kind of spin locks also in Windows operating systems, for instance, but I don't really trust them because then comes an update and everything changes, and maybe a new Windows version of Windows, and it's not well documented. So I I would recommend using the spin lock implementation that Intel recommends, which is just like 10 lines of assembler that or mostly C with some inlining stuff. Just use that and you're fine. Actually, I thought, well, I write my own, and it was so buggy it almost fucked up the whole demo. But so please use the Intel version. They know what they're doing. We have the spin locks. Oh, actually, it is a good idea at the end of the frame, when you're done, to yield to the operating system. Two reasons. First, if you're running on a laptop, that will save battery life. The second reason, the operating system will insist on doing some backward task, and maybe it's better you give it a chance to do that backward task, so it doesn't happen in the middle of the frame, but when you have nothing to do with your course anyway. So yielding once a frame, I would say no problem, but yielding all the time, big disaster. So if you're using these spin locks, well, I say lock rarely, lock quickly, and never yield, of course. Because you don't want to have all your threads waiting on each other. And the best way to do that is, well, not to lock at all, which is very difficult to do, so please, well, advanced topic. Or at least lock as rarely as possible and as quickly as possible. so that the chances of that these tasks actually wait on each other are as small as possible. If you're really going for high performance, you should be aware of sharing memory problems. As long as all your threads only read from memory, nothing is a problem because every core has its own cache. But if one core writes something, it has to invalidate the caches of all the other cores with L1 and L2 cache and possibly L3 cache, and this can be a very expensive thing. So if you lay out your memory structures, make sure that if it is possible, that they don't always write to the same cache lines. For instance, if you have a flag per thread, which is only 8 bits, don't put them next to each other, but space them apart so that every thread has its own cache line and they don't collide that much. This is done per cache line. This is an important thing to remember. So much for basic multi-threaded programming, which is actually, if you got your logs right, pretty simple. Just log everything and be sure that you don't mess it up. So now what we now need is a scheduling engine. We have all these thousands of tasks. We have our 4 threads. Now we want to distribute the workload. And the simple solution for that is, of course, you have a list of tasks, and each thread picks the task and removes it from the list, one at a time. And, of course, that is not what you want, because then you have, imagine the sound effect, no! Then you have a single bottleneck in your whole system. And if you have many, many cores, they will all try to get this log, to get to this list, and pick tasks. And it just won't scale. So a more clever solution to the problem is a system called task stealing. And actually, it's a system that Intel also uses in their threaded building blocks. The idea is not have a big list of tasks, but have a queue of tasks for each thread. And you see, this is a game, and we have 6 cars on the track, and maybe 10 effects that have to be handled. And each task can pick, each thread, I'm always confusing thread and task, please excuse that. Each thread can pick a task, and there's no sharing of memory or tasks. They have their own log for each queue, and there's no possibility that this system can stall if you do it like this. Until the moment when one thread gets empty. Obviously, these car tasks are pretty easy in this example, while the effect tasks are a bit more heavy. And how task stealing works is the main thread now picks another thread, like, for instance, thread 3, splits its workload, and steals it. And in this moment, we have an interaction between main thread 0 and thread 3 and maybe all the other threads, because he has to figure out which one is the best victim for stealing. We have also some interaction going on, which might cause some stalls, but we only have to do it rarely, because once we have stolen something, we can continue just easily. In a real-world scenario, there will be some end game where they're all stealing from each other because everyone is running out of work. But it's a lot less interaction as if we have a single list and everyone has to pick, and every time there has to be a log. So much for a task stealing engine that will actually work. I have a simple example, a very simple example. Well, it doesn't look so good. Well, you can see the essential things. I have made 512 tasks. Each line of this Mandelbrot set is a task. And these tasks are scheduled to 4 threads, and each thread marks its line with a color code so that we can see which thread is used to do this line. And you can see some initial allocation going on here with obviously the blue thread gets the first quarter, the red thread gets the second quarter, the green thread gets the third quarter, and the yellow thread gets the lowest quarter. And let's stop it. This is a good. This is the key to stop it. Obviously, every line takes a different amount of time because these black areas take more time to calculate, and so it has to rebalance all the time. We can see here the yellow thread starts doing its lines, but the blue thread finishes first, then the blue thread steals from the green thread. And then the green thread steals from the yellow thread. And so more and more stealing goes on until all the lines are rendered. And well, with this example, we can check very nicely how the load is balanced in a wonderful way. Unfortunately, those labels up there are not working, but in the next example, they will be working. Some details. First of all, it seems like a very bad idea. If I have to create 512 tasks, I don't want to make a loop creating 512 task structures, putting them in a queue. This doesn't sound like a high-performance way of doing it. So if you're designing such a system, it is a good idea to allow a task to have subtasks, so that you only create one task structure with subtasks 0 to 511, and then you can split that into tasks and so on. This reduces the number of structures you have to create during a frame dramatically. Because you only have to create a new structure once at the beginning, and then each time you split something. The next thing, I said there are two decisions a task-stealing engine has to do. The first decision is find out from whom to steal the task. The second decision is how to split the list of tasks. So let's go to the first one. How to figure out which thread to split. Each thread has a queue of tasks, and we have to pick one victim. And now imagine you have 64 cores, and you don't want, each time you want to split, lock 64 threads, figure out how much work there's left, then steal from it, and then unlock them all. That would be a disaster. But there are two tricks. The first trick is we don't have to lock them all. We can just peek at them, how many workloads they have left, how many subtasks, for instance, as a measure, the number of subtasks, not being concerned on how long a subtask might take, just the number of subtasks. Just peek, take the one with the highest count, and then you lock that. The problem is, the time you lock that, the task might have gone away because somebody else stole them, or the task itself did it. But that's something we can simply ignore. We try again until there's nothing left. This happens so rarely, we can ignore that. So the first idea is don't lock all the tasks, just peek at them and then pick one, and maybe it's gone, well, don't care. The second idea, to limit the number of tasks to peek at, because that still doesn't scale very well, is, well, I don't have to actually peek at every task, at every thread. Sorry, I'm always confusing these two words. I don't have to peek at every thread. It's okay if I peek at log 2 threads. For instance, my thread has a thread ID called ID, and then I peek at threads ID XOR 1, ID XOR 2, ID XOR 4, ID XOR 8. So I'm only peeking at a very limited set of tasks. But this pattern will ensure that eventually the tasks will get spread all around. Also, if in my initial peeking I don't find anything, then I can still look at everyone. In this way, I can select a thread to split without having to look at everyone, every time. The next problem is selecting where to split the load. In a perfect world, I would have to look at every task in the queue, figure out how many subtasks there are, and then calculate the best split point. But that's not really necessary. You can just, if there's more than one task, with many subtasks possibly, just split at task level. If there's only one task left, split at sub-task level. And that's working well enough. You might need a few more splits, but splits are cheap, so no problem. Another thing to notice is I made an initial distribution here, especially in my slides. That's not really necessary. You can use the normal splitting mechanism. Here we had this initial distribution. We can use the normal splitting algorithm to get to this initial distribution, and then it will be in parallel, which is, of course, a lot better. It won't matter with 8 cores, but with 64 or 1,000 cores, it would matter. Yes. So now we have a task stealing engine that distributes our tasks to all those threads, does it in a pretty efficient way, and is utterly useless because we can't model dependencies. We need a way to model dependencies. And the simplest way to do that is to allow a task to spawn other tasks. They can spawn them in their own thread. It will be a very cheap operation because you're not having to lock other threads or something like that. And if a task can spawn other tasks, you can simply make something like an octree traversal. You have 1 to n dependencies modeled out. And having recursion and recursion working, that is a good thing. But that's not all we need. We also need a possibility to wait for, let's say, if you are doing a merge sort, then you have a point where you split into 2 tasks, which do, that's the recursion. And when both of these tasks finished, then you have to merge. So we need to find out a way to how we can model these 2 tasks have finished and then spawn a new task. And this can be done with a very simple structure I call it a sync, a synchronization point. You just have, a sync is just a counter and a pointer to the task that you want to start. And each task at the end can decrease that counter, and when that counter is 0, the task gets spawned. In this way, we can easily do n by m dependencies. If these 7 tasks have finished, we spawn these 6 tasks. So we can express any dependency there's likely to be. I can show the merge sort example. This is doof. You see, this doesn't work. The cube has nothing to do with the merge sort. All we have to look is at this. Down there, we can see many, many little tasks getting executed. He's sorting a set of 1,000,000 points. And the blue bars that are the splitting, and the pink bars are the merging. And the red bars are waiting around. This is a better example. And you see at the end there's a lot of non-parallel merging happening. Especially the last merge will never be in parallel, of course. You can also see that there's a room for improvement. Well, that's the pattern of the merge sort. This would be the non-parallel version, which is used for smaller arrays in the parallel version. And I don't know why the cube is black. It should be green. So finally, we have a system that is really powerful. We can express any dependency there is. And still, that was a much too simple example. If I render when I rendered the Mandelbrot set, each task knew exactly where it should write its data. But imagine I was doing something like marching cubes. And every task is responsible for a cell in space. There's no way in advance to tell how many vertices are generated by that cell. It may be 0, it may be very likely be 0, but it may also be quite a lot. It would be insane to allocate a memory buffer to each cell which can hold the maximum possible number of vertices generated. It would also be insane to have a vertex buffer generated by each cell and have thousands of vertex buffers. That DirectX wouldn't like that. So we need to find a way how we can make all these tasks merge their data into a big vertex buffer without knowing in advance how much bytes each task will generate. And we can't do it with a single vertex buffer, but we can do it if we have a vertex buffer for each thread. Then each task can just append to the thread's vertex buffer, and in the end we have only a vertex buffer per thread, which is okay. Actually, even then it might get a little bit very unbalanced if certain threads generate less polygons. What I would do, or what I have done, is that there's a pool of vertex buffers, all pre-initialized, pre-mapped, and each thread picks from this pool a vertex buffer, enters its vertices, and when it's full, it picks another one. And this way, well, we require synchronization every time a thread picks a vertex buffer, but that's only a few times, maybe 20 times or so. Shouldn't be highly contended place to do. We can have it here, marching cubes. And down there we see all those. Those are quite a lot. This is an insane amount of tasks going there. Another interesting idea is to say, well, just increase the granularity, and then I don't put such a load on the task seeding engine, but it doesn't make such a difference. This engine really can handle an insane, if you look at the FPS, it can handle an insane amount of tasks. This is hex 2,800, 10,000 tasks or so. If you increase the granularity too long, you see that red bars back there. You waste some processing if you make it too granular, obviously. This is not a good idea. Also, you see, at the moment, 8 times, 10 times the stealing happens. You have to read it like this. 8 times stealing, and it never fails. Sometimes a lock is picked, but that has already been locked. Or I locked so rarely here that I almost have no lock contention. Yeah. So we can emit lots of vertices, although we don't know how many we emit. We have solved this problem that we don't know how much data each task will generate. But that was a way too simple example because we didn't care about the order of the data. There's another problem. Maybe you are familiar with DirectX 11 deferred context rendering, which basically means that usually all your calls to DirectX will be done by the main thread. If your calls to DirectX were be made by multiple threads, they would happen in a more random order, and DirectX wouldn't know which order was the correct one. Maybe your render calls ended up in the wrong render target. That would be pretty disastrous. Maybe they're just in the wrong order and the transparencies are wrong. You need to do your draws in the correct order, unlike with the marching cubes, where order was not an issue. And the solution from DirectX is that every thread gets its own context where it can render in, and then the main thread appends these contexts so that the order is in a very defined state. There's no ambiguity about the order which is meant. Still, we have the problem. If we use the example from above, with deferred context per thread, that the tasks would emit their draw commands in a random order. So we have to figure a way out to do that. Now, usually you would use a multi-threading engine, a task scheduling engine that you buy, for instance, from Intel. It's for free, it's a good one, it's much better than mine. But then you don't really know what happens inside. But since I wrote my thing myself, I know exactly what happens inside. And actually, the tasks are not that mixed up. It's not like you take a deck of cards and then you mix it like this, and then everything is a random order. It's more like you take a deck of cards and do a couple of shuffles, and actually the cards aren't really in a random order. They're just almost random. They're consecutive runs of tasks which are in order. So what we can do is use that. Oops. And it works like this. Each task has a number, of course. And my thread gets task 0. Okay, start a new deferred context. Put in the stuff for task 0. Then it gets task 1. Okay, put in the stuff for task 1. Task 2, append task 2. Task 3, append task 3. Task 10. Put back the whole context, which is in order in itself. Get a new context and start over with task 10, task 11, task 12. So every time a thread encounters a task that is out of order for this job, it starts a new deferred context. We end up with a couple of deferred contexts, not thousands, which we can easily sort and execute. So even though the task stealing engine mixes up our task pretty bad, it's not so bad that we can't reorder it easily. I also have a very boring example made for this. Here we can see the blue part is where all these cubes are drawn in a single draw index primitive. Very bad thing to do, but I did it anyway. And the yellow bar is actually, the problem is with this graphics card I have in here, the whole feature of deferred context is not in the driver, so DirectX has to work around it. And the yellow bar is DirectX taking all these deferred contexts and unmantling it and doing their stuff. But, well, we can preserve the order of these calls. What I don't like, I want to go a little bit more extreme here now. Wrong mode. Here you can see we have some cyan, this color cyan things to do. After that is done, we can start the blue task, and in parallel, I start a bunch of yellow tasks, and when that is done, I can start the green task and the cyan task. So we have here we have a graphics pipeline where that blue stuff depends on the cyan stuff, and that green stuff depends on that yellow stuff. And what I don't like is this synchronization period here. How can we get rid of this? And if we would just put the green and the yellow tasks into the same pot, something like this would happen. They got all mixed up. Now I don't have any blank room between the cyan and the yellow task, but the blue task gets started much too late. So what would be cool would be a way to prioritize the cyan task before the yellow task so that they don't all get mixed up. And actually that is possible. Here you see that no time at all is wasted. Once the cyan tasks are done, the yellow starts, the yellow tasks fill all the gaps in the cyan task, the blue tasks get started, and there's also no gap on the other end. So we have no wasted time here. But how can we express priorities in such an engine? This is the last problem in this talk. First, I want to define the problem very clear. This is a little bit confusing. Workload I should be finished as fast as possible. Workload B, this is the yellow stuff, can be used to fill the gaps. But even workload I might be empty, but still executing the last task. And that last task might spawn a bunch of other tasks. So even if workload I is seemingly almost empty, and only one task is working on one thread, and all the other threads are still working on workload B. Even then, workload A tasks come again, and they must push aside the workload B tasks. We need to prevent the task from workload B to push aside workload A. That's the problem here. And if we put all the tasks, the A tasks and the B tasks, in the same queue, they will mix. There's no way. So the solution for this is have different queues. We have a queue for each thread already, so that having a single list of tasks would be bad. And now we say we have, for each thread has a queue for each workload. If we have priorities, we have many workloads, and then each of these workloads has its own queue of tasks. And if we only fetch from the top workload, this workload A in this case, these are prioritized. Only if the top workload is temporarily empty, then we fetch from the other workloads. And we perform the splitting, of course, inside the workload, so they don't get mixed up. And this way, we can express priorities and solve that last problem that I encountered. And that actually is it, what I wanted to talk about. Sorry, there's just one more thing. We can watch that demo that's running outside, but with debugs on. It's a little bit awkward that they're running the same stuff here, you know. But oh, that's Rove. Sorry. I'm talking about this one, Magellan, which of course uses heavily the multithreading. This, of course, is a fake. During the progress bar, we are almost no multithreading running. So this whole progress bar thing is just a fake to get you in the mood, and it's taking eternities, obviously. But it does count the number of cores. So that if you get a 12-core machine, you actually have 12 bars. I tested it up to 64. I don't know what happens beyond that. So, dum-de-dum, now he's warming up the caches. Dum-de-dum. Come on. You can make it. This is my laptop. It's not the fastest machine. First one to know is you can press F1, then you get the menu, and you can the frames per second, and most importantly, the multi-threading debugger. We skipped this part because the markers for the debugger are not set correctly. Jump. Here's no multi-threading going on. CPU is doing almost. Can you turn down the volume a bit? Is anybody back there? No multithreading going on. But here you have the green stuff. The yellow stuff is the physics, and the green stuff is the marching cubes effect. And the red stuff again is the base. Now we have 2 times the effect. It's actually all done twice. This is pretty. Here we see more physical yellow stuff, and again the green stuff is the marching cubes. All the same. Just skip through it. More of the same. Here we have this water blob. Here again, it's just GPU power, all these transparencies that cost a lot. And here we have only the physics without the marching cubes, so it's only the yellow. You see how he's doing multiple simulation steps in each frame. And here he's doing only the marching cubes, but in the end the object doesn't morph anymore. Then we can switch off the marching cubes, and then we can have two of them. And here really complicated things are going on. The first thing is, if I pause the demo, it doesn't take any time anymore. Again, he's using marching cubes to create all these fractals. This is not a ray tracing thing, it's real polygons. And the big pink bar is the GPU creates the ISO points. It calculates all the ISO volume points. Then they are transferred to the CPU, which is the big stall. But during that stall, I can use the other threads to render the marching cubes. Here, I cache all these tiles. So only when new tiles come into the screen, I actually have to do the work. Because it's polygons, I can cache them for multiple frames. And you see the first transfer makes a big stall, the second transfer or the third transfer only makes small stalls. That's just because of DirectX 9. With DirectX 10, that would have been no problem to avoid these stalls. Yeah, that was multithreading in action. Now I'm really finished, sorry. Don't need the slides. Okay, any questions?
Yeah. Hello. Yeah. In the really beginning, you showed the very primitive scheduling way of creating a set of tasks, and every worker thread would have to steal or lock the main thread to get a task.
Yeah.
There's a lock-free way with interlocked increment. You have an array of tasks, and you interlock increment task ID.
But you still have the memory sharing.
Yeah.
And you could also add tasks to that system. Yes, it's not only the lock, it's also the memory sharing. But you're right there, yes.
Okay. I just wanted to ask what's the benefit of this task stealing, but afterwards in the slide you showed how many different optimization techniques you can use.
Yeah. Also, if the way the tasks would be randomized would be different, and I couldn't reassemble them correctly, that would be a problem.
Yeah.
So what does your task structure look like? Do you have like a fixed number of parameters? And how do you allocate these task structures? Do you have like an allocator per thread, or?
There's an allocator per workload, and that's using lockless stuff. But you can do it. The task structure really is nur 2 pointers. There's nothing much about it.
Okay. So you would have like a structure for the parameters in case you need more parameters for
the parameter structure is not part of the task scheduling engine.
Okay.
But there's a helper function that allows you to allocate any amount of memory, small amounts of memory.
Sure.
Everything else you should prepare in advance, like the vertex buffers are all prepared in advance.
Okay, thanks.
Hi, did you consider to compare your performance to the MPI or OpenMP implementations? I mean, I know why you are doing this, but this is also possible to do it with some API.
I'm pretty sure something like Untitled building blocks will perform much better than my solution. But the idea of Untitled building blocks is to scale to thousands of cores in the end. And as a game programmer or a demo programmer, I don't have that problem. Because if my game doesn't run well on 8 cores, no matter my game has to run on 8 cores. So if the guy has 16 cores, well, all the better. But I don't have these scaling problems. I don't have to scale to infinity. Yeah, so I don't really need all the cool stuff that's in Untitled building blocks. I'm not saying that you should write your own code. I'm just saying that it is possible, it's fun, and it would be hard to do all the stuff that I did if you don't know exactly what's inside the engine. I know that Untitled building blocks is very customizable, so that it should be possible to get the same results with it. There's another reason. It's size. I really don't like the idea of linking a huge template library into my code. It creeps. Then you've got that library, and that library, and that library, and then you've got 20 libraries, and each of one has their own sub-libraries with primitives. I really hate that. I more like libraries like stbimage, which is just one file, and you link it, and you can load JPEGs without worrying about anything. That would be cool, but Untitled building blocks isn't that kind of library. It's this monster library, and I don't like that.
Okay, thank you.
So I assume that you are locking each thread to a core, right?
I'm not fiddling around with Microsoft's scheduling decisions. So I just start the right amount of threads and let Windows do the business. Because, for instance, I noted just going from Windows 6 to 6.1 it totally crashed my engine because of some subtle changes they made. So I don't want to do too much with thread priorities and affinity masks. I don't do that.
And so how often does the system break your thread to run something? Have you tried, for example, keeping one core for the system and the rest for your demo?
I tried that. Actually, the demo Magellan has a button where you can switch on, keep one core for the system. When my task scheduler was very buggy, that button made a huge difference. But then I fixed it, and now it just makes things slower. But it's always good to have such a button in your dialog box.
Thanks. Thanks.
No further questions.
No further questions. Thank you very much.